process that is dramatic but slow, measurable, and in the deepest sense, natural. I am talking about a different kind of threat. A threat that arrives not gradually, but suddenly. Not over millions of years, but in a matter of seconds. A burst of energy so intense that it could strip the protective chemistry from our atmosphere in the time it takes you to draw a breath, exposing the surface of this planet to radiation levels that no complex life could survive. The star that poses this threat is currently burning right now, as you read these words. It is approximately 7,500 light years from Earth. It is one of the most massive, most luminous, and most unstable objects in our galaxy. It has already undergone a catastrophic eruption that briefly made it the second brightest star in the sky, visible in daylight from the southern hemisphere before it faded back to relative obscurity. And when it finally collapses, when its nuclear fuel is exhausted and its core implodes in less than a second, the explosion that follows could produce a beam of radiation so intense that it would arrive here carrying more energy than the sun delivers to Earth in hundreds of thousands of years, concentrated into a pulse lasting seconds to minutes. The star's name is Eta Carinae, and I want to tell you everything about it. Not to alarm you in a way that is disproportionate to the actual risk, because I am going to be honest about the uncertainties and the timescales and the probability that Earth is in the danger zone. But because the story of Eta Carinae is one of the most extraordinary stories in all of stellar astronomy, it connects to the deepest physics of how stars live and die, to the history of mass extinctions on Earth, to the question of what the cosmic environment of our solar system actually looks like when you examine it with the full precision of modern astrophysics. And it raises a question that I find genuinely important and genuinely unsettling. We live in a universe where the most violent processes in nature can affect us across thousands of light years, and the specific star that poses the most precisely characterized of those threats is visible in the sky tonight to anyone in the southern hemisphere standing under clear, dark skies. Let me begin with the physics of why massive stars are dangerous. Because to understand Eta Carinae, you need to understand what massive stars do, why they live fast and die violently, and why the violence of their deaths can propagate across the galaxy in ways that threaten planets they have never directly interacted with. The life of a star is, at its most fundamental level, a negotiation between two forces. Gravity, which pulls all the stellar material inward toward the center, and the outward pressure generated by nuclear fusion reactions in the core, which resists that inward pull. For most of a star's life, these forces are in balance. The star maintains what physicists call hydrostatic equilibrium. The pressure from the core exactly counteracts the weight of the overlying layers. The star is stable. This balance is maintained by nuclear fusion. In the core, hydrogen nuclei, protons, are fused into helium nuclei. The fusion releases energy because the helium nucleus weighs slightly less than the 4 protons that combine to form it. That missing mass is converted to energy according to Einstein's equation, and the energy flows outward through the star, producing the pressure that holds it up against gravity. The sun has been doing this for 4.6 billion years. It will continue for approximately another 5 billion. The fusion is steady, the pressure is stable, the equilibrium is maintained. But this equilibrium depends on the continuous availability of fusion fuel. Stars do not have unlimited hydrogen. They burn through it steadily, converting it to helium over their main sequence lifetimes. And when the hydrogen in the core is exhausted, the balance is disrupted, the pressure drops, gravity reasserts itself, the core contracts, and as the core contracts, it heats, the temperature rises until new fusion reactions become possible. Reactions between helium nuclei that produce carbon and oxygen, the star adjusts. A new equilibrium is established. But the star is not the same star it was before. It has changed. This sequence, the exhaustion of one fuel and the ignition of the next, repeats multiple times in the life of a massive star. Each stage requires higher temperatures and higher densities than the one before. Each stage lasts for a shorter time. Hydrogen burning, the longest stage, might last millions of years in a massive star. Helium burning lasts hundreds of thousands of years. Carbon burning lasts thousands of years. Neon burning lasts years. Oxygen burning lasts months. Silicon burning lasts days. The star is rushing toward its end, burning through its remaining fuel at an accelerating rate, each new fuel more desperate than the last. And then silicon burning produces iron. And iron is where the story ends, because iron is different from every element that came before it. Iron has the most tightly bound nucleus of any element. Fusing iron into heavier elements does not release energy. It consumes energy. A star that begins to accumulate an iron core in its center is no longer generating pressure to hold itself up. It is draining its reserves. And when the iron core reaches a critical mass, approximately 1.4 solar masses, gravity wins. The core collapses in less than a second, from a sphere the size of the Earth to a sphere 20 kilometers across. The matter in the core reaches nuclear density, approximately 250 trillion grams per cubic centimeter. Individual protons and electrons merge to form neutrons through a process called inverse beta decay, releasing an enormous flood of neutrinos. The collapse releases an astonishing amount of energy, roughly 3 times 10 to the 46 joules, more energy than the sun will emit over its entire 10 billion year lifetime, almost all of it in the form of those neutrinos emitted in a pulse lasting a few seconds. And the infalling outer layers of the star hit the incompressibly dense neutron star surface and bounce outward in a shock wave that, combined with the energy deposited by the neutrinos, tears the star apart in a supernova explosion. I want you to pause for a moment on those numbers. 3 times 10 to the 46 joules in a few seconds. The sun's total luminosity, its energy output per second, is approximately 3.8 times 10 to the 26 watts. The sun will emit that luminosity for 10 billion years. Over its entire lifetime, the sun will radiate approximately 1.2 times 10 to the 44 joules. A core collapse supernova releases 300 times that energy in a few seconds. The neutrinos alone, the invisible, weakly interacting particles that most matter barely notices, carry more energy in those few seconds than the sun radiates visibly over its entire existence. Even more extraordinary is the fact that the neutrino pulse from a supernova in the Milky Way would be directly detectable on Earth. In 1987, when a star in the Large Magellanic Cloud, a satellite galaxy about 165,000 light years from Earth, underwent core collapse and became supernova 1987A, neutrino detectors in Japan and the United States and the Soviet Union recorded a burst of neutrinos lasting approximately 12 seconds, slightly preceding the optical brightening. 24 neutrinos were directly detected in detectors containing thousands of tons of water, out of the roughly 10 to the 58 neutrinos emitted. The detection confirmed that the core collapse picture was fundamentally correct. The neutrinos arrived before the light because they were produced deep in the collapsing core and escaped immediately, while the light had to diffuse through the overlying stellar material. If Eta Carinae were to undergo core collapse, the neutrino burst would arrive here before the visible explosion, and neutrino detectors around the world would see a flood of events. This would provide a few hours warning before the visible supernova brightened to its peak, though of course not enough time to do anything in response. This is the standard picture of how a massive star ends. The supernova releases an enormous amount of energy. In the optical, invisible light, a supernova at this distance would briefly outshine the entire Milky Way. The explosion disperses the heavy elements built up in the star's interior, the carbon, oxygen, nitrogen, silicon, iron, and all the elements built up in the supernova itself into the interstellar medium. These elements eventually become part of the next generation of stars and planets, and in at least one case we know about, part of organisms capable of asking about the process. But the standard picture, as extraordinary as it is not the most dangerous version of what can happen when a massive star dies. There is a more energetic, more directed, more specifically threatening process that can occur in specific circumstances, and that process is the gamma ray burst. But the standard picture, as extraordinary as it is not the most dangerous version of what can happen when a massive star dies. There is a more energetic, more directed, more specifically threatening process that can occur in specific circumstances. And that process is the gamma ray burst. There are two main types of gamma ray bursts, distinguished by their duration and their physical origin. Short gamma ray bursts, lasting less than 2 seconds, are produced by the merger of two compact objects, typically two neutron stars or a neutron star and a black hole. These mergers are the same events that produce gravitational waves, and the landmark detection of GW 170817 in 2017 was accompanied by a short gamma ray burst that confirmed the connection between neutron star mergers and this class of event. Short gamma ray bursts are less energetic than long ones and pose a less severe threat at any given distance. Long gamma ray bursts, lasting more than 2 seconds and often lasting minutes, are the type that Eta Carinae might produce. They are associated with the core collapse of massive stars, specifically with a class of supernovae called hypernovae or type ICBL supernovae, characterized by unusually broad spectral lines indicating high velocity ejecta. These supernovae produce the most energetic explosions in the known universe. The isotropic equivalent energy of a long gamma ray burst, the energy that would be released in all directions if the emission were isotropic rather than beamed, can be as large as 10 to the 47 joules, comparable to or exceeding the total gravitational binding energy released in a standard core collapse. The beaming of this energy into a narrow jet is what makes long gamma ray bursts so dangerous at large distances. If the total energy of the burst is concentrated into a beam with an opening angle of, say, 5 degrees, the area of the beam at a distance of 7,500 light years is a circle roughly 1,300 light years in diameter. The energy fluence within that beam is orders of magnitude higher than it would be if the same energy were distributed isotropically over the full sky. This beaming is why gamma ray bursts are detectable across the observable universe despite being produced by objects that are millions of light years away. We only detect bursts whose beams happen to be aimed at us, which means we see only a small fraction of all the gamma ray bursts that occur. The true rate of gamma ray bursts in the universe is much higher than the detection rate suggests, because most bursts are aimed away from Earth. This beaming also means that the probability of Earth being in the beam of any given nearby gamma ray burst is small. The fraction of the sky covered by the beam of a typical long gamma ray burst is approximately the opening angle squared divided by 4, which for a 5-degree opening angle is roughly 0.2%. The probability that Earth happens to lie within that 0.2% of the sky from Eta Carinae's perspective is roughly 0.2%. This is the geometric factor that reduces the risk from even the most extreme nearby gamma ray burst candidate to something manageable rather than immediately alarming. But 0.2% is not zero. And Eta Carinae is an unusually energetic potential source at an unusually close distance. The combination of proximity and potential energy output is what puts it in a different category from other massive stars in the galaxy. A gamma ray burst is the most energetic electromagnetic event in the known universe. It releases in seconds to minutes more energy in gamma rays than the sun will emit in its entire lifetime. All of it, or most of it, concentrated into two narrow beams directed along the rotation axis of the collapsing star. The beams carry gamma radiation, the most energetic form of electromagnetic radiation, at nearly the speed of light. And the fluence, the total energy deposited per unit area at a given distance from a gamma ray burst at 7,500 light years from Earth, if the beam is aimed in our direction, is sufficient to cause serious damage to the ozone layer. Let me be precise about what that means physically. The ozone layer is not just a convenient shield. It is the chemical buffer that makes complex life on the surface of the Earth possible. Without the ozone layer, the full intensity of the sun's ultraviolet radiation would reach the surface. Ultraviolet radiation at those levels disrupts DNA, inhibits photosynthesis, and kills unshielded organisms. The ozone layer, a thin layer of ozone molecules at altitudes of approximately 15 to 35 kilometers, absorbs the ultraviolet and prevents it from reaching the surface. We exist in a very direct sense because of the ozone layer. When gamma radiation from a nearby gamma ray burst enters the atmosphere, it interacts with nitrogen and oxygen molecules in the upper atmosphere, producing nitrogen oxide compounds. These compounds catalytically destroy ozone. The chemical cascade triggered by a single gamma ray burst from a source within a few thousand light years could reduce the ozone column by 20 to 40% or more, depending on the total energy deposited and the specific atmospheric chemistry at the time. An ozone depletion of that magnitude would significantly increase the ultraviolet flux at the surface, with consequences for surface life and for marine photosynthesis that could persist for years or decades after the event. The specific calculations are complex and depend on many parameters, including the total gamma ray fluence, the duration of the burst, the existing state of the atmosphere, and the geographic distribution of the effects. But the qualitative picture is well established. A gamma ray burst from a nearby source, if Earth is in the beam, is a major environmental perturbation. Not necessarily an extinction level event for all life, not necessarily the end of everything, but something that would fundamentally disrupt the biosphere for years to decades and could cause the extinction of a significant fraction of species, particularly those most dependent on sunlight and photosynthesis. Let me be more specific about the physical mechanism, because I think it is important to understand precisely how gamma radiation from a distant star interacts with our atmosphere. When a pulse of gamma radiation enters the atmosphere at high altitude, the individual photons, each carrying energies of millions to billions of electron volts, collide with nitrogen and oxygen molecules. These collisions produce a cascade of secondary reactions. The gamma photons dissociate oxygen molecules and nitrogen molecules into their constituent atoms. These atoms recombine in various ways, including forming nitrogen monoxide, nitrogen dioxide, and other nitrogen oxide compounds that are collectively called NOx. The NOx compounds are catalysts for ozone destruction. A single nitrogen oxide molecule can participate in thousands of ozone-destroying reactions before it is eventually removed from the atmosphere. In the catalytic cycle, nitrogen monoxide reacts with ozone to produce nitrogen dioxide and ordinary molecular oxygen. The nitrogen dioxide then reacts with an oxygen atom to produce nitrogen monoxide and molecular oxygen again. The net effect is the conversion of ozone into molecular oxygen, with the nitrogen oxide acting as a catalyst that is regenerated with each cycle. This cycle, once established, can remove ozone from a large volume of the stratosphere very efficiently. A gamma ray burst with a total isotropic energy equivalent of approximately 10 to the 44 joules at a distance of 7,500 light years from Earth, with the beam aimed at us within its characteristic opening angle, would deposit an energy fluence at Earth's upper atmosphere sufficient to produce NOx concentrations that could reduce the ozone column by 20 to 40% or more. The reduction would not be uniform. It would be most severe at latitudes directly in the path of the beam, with effects decreasing toward higher and lower latitudes. But even a 20% global reduction in ozone column depth would significantly increase the ultraviolet B flux at the surface, with consequences that would be felt by every organism dependent on photosynthesis or sensitive to ultraviolet radiation. The ozone would eventually recover. The NOx compounds are removed from the stratosphere by chemical reactions and by transport to the troposphere, where they are rained out. Recovery of the ozone layer after a major perturbation takes years to decades, depending on the severity of the depletion and the atmospheric chemistry at the time. During the recovery period, the biosphere would be experiencing elevated ultraviolet fluxes. Some organisms would die, others would survive with reduced productivity. Ecosystems would be stressed. Whether the stress would rise to the level of a mass extinction depends on the specific severity and duration of the ozone depletion and on the state of the biosphere at the time. We should take this seriously. Not because Eta Carinae is about to explode tomorrow, but because it is the best characterized nearby candidate for such an event, and because understanding it tells us something important about the cosmic risk environment in which life on Earth has been developing for 4 billion years. Now let me tell you what Eta Carinae actually is, because the description requires some extraordinary numbers. Eta Carinae is located approximately 7,500 light years from Earth in the southern constellation Carina, the keel of the mythological ship Argo. Its distance is known with some uncertainty, with estimates ranging from roughly 7,200 to 8,000 light years, but the best current measurement puts it at approximately 7,500. It was cataloged by the astronomer Edmund Halley of Halley's Comet fame in 1677 during an expedition to the South Atlantic island of St. Helena. At that time, it was a moderately bright star, around 4th magnitude, unremarkable among the thousands of southern hemisphere stars Halley was cataloging. Nobody at the time suspected what it was. In the following century, Eta Carinae brightened gradually. By 1820, it had become one of the brightest stars in the southern sky, 1st magnitude, comparable to the brightest stars visible from Earth. But that brightening was only the prelude to something far more dramatic. In April of 1843, Eta Carinae underwent what astronomers now call the Great Eruption. Over a period of months, it blazed to a peak brightness that made it the 2nd brightest star in the entire sky, surpassed only by Sirius. It would have been visible in daylight from locations with a clear southern horizon. Sailors navigated by it, astronomers observed it with the best instruments of the era. And then, over the following decades, it faded. By 1870, it had dropped below naked eye visibility. By 1900, it required a small telescope. For most of the 20th century, it was an object for specialist observers, known to be extraordinary but not prominent in the sky. What happened in 1843? We now understand it as a massive stellar eruption, not a supernova, because the star survived it, but an event that released energy comparable to a supernova in terms of the light and matter expelled. Over the course of the eruption, Eta Carinae expelled a mass estimated at 10 to 20 times the mass of the Sunday. That expelled material, moving outward at several hundred kilometers per second, is now visible as the Homunculus Nebula, a double-lobed cloud of gas and dust surrounding the star. The homunculus is approximately 1/3 of a light year across. If you could see it with sufficient magnification, it would appear as a peanut-shaped cloud glowing in the infrared, with the star at its center. The scale of the 1843 eruption is almost impossible to convey in ordinary terms. Consider what it means to expel 10 to 20 solar masses in a few years. Our sun has a mass of approximately 2 times 10 to the 30 kilograms. Eta Carinae expelled 10 to 20 times this mass, meaning 2 to 4 times 10 to the 31 kilograms over perhaps 3 to 5 years. To move this mass outward at speeds of several hundred kilometers per second requires kinetic energy of approximately 10 to the 44 joules. This is comparable to the total energy released in a standard core collapse supernova. Eta Carinae released supernova-level energy in 1843 and did not die. It survived. It continued to exist as a star. This is extraordinary and still not fully explained. The luminosity of Eta Carinae during the peak of the Great Eruption approached 10 million times the luminosity of the Sunday. For a few years in the mid-19th century, this single star was emitting more energy and visible light than all the other stars in the Milky Way combined. The star's bolometric luminosity, its total energy output at all wavelengths, was even higher, since much of the emission at peak was absorbed and re-radiated by the expanding shell. Astronomers in the 19th century, observing with the naked eye and with early telescopes, saw a star that blazed in the southern sky like a second, dimmer Sunday. They had no theoretical framework to explain what they were seeing. The astrophysics required to understand LBV eruptions would not be developed for more than a century. The mass of the homunculus, 10 to 20 solar masses expelled in a few years, is staggering. Our sun has been radiating energy for 4.6 billion years and will continue for another 5 billion. Over its entire lifetime, it will radiate energy equivalent to the mass conversion of about 0.1% of its total mass. Eta Carinae, in a single eruption lasting a few years, expelled a mass 10 to 20 times the sun's entire mass. This is not a normal stellar wind. This is not the kind of gradual mass loss that most massive stars undergo over their lifetimes. This is something qualitatively different, a paroxysm of stellar violence that we do not fully understand and cannot currently predict. The cause of the great eruption of 1843 is still debated. The leading hypothesis involves the instability of a star near the Eddington luminosity, the theoretical maximum luminosity beyond which the radiation pressure from a star's interior would blow the outer layers away. Eta Carinae is close to this limit at all times. Near the Eddington limit, the balance between gravity and radiation pressure becomes unstable. Small perturbations can grow into large oscillations. The star can undergo violent pulsations that temporarily breach the Eddington limit and expel enormous amounts of mass. This is called an LBV eruption, for luminous blue variable, the class of extraordinarily massive and luminous stars to which Eta Carinae belongs. But the 1843 eruption may have had an additional complication. Eta Carinae is not a single star. It is a binary system. The primary star, the hypergiant that drew all the historical attention, has a companion, a massive star in its own right, roughly 30 solar masses orbiting in a highly elliptical orbit with a period of approximately 5.5 years. The orbit is eccentric enough that at closest approach, the two stars pass within a few astronomical units of each other, close enough for their stellar winds to interact violently. The interaction of the two stellar winds at closest approach produces a collision region of X-ray emitting plasma that varies in brightness and spectrum predictably with the orbital period. This orbital variation was only discovered in the late 20th century using X-ray telescopes that were not available to 19th century astronomers. Some researchers have proposed that the 1843 eruption was triggered or amplified by a close encounter with the companion star. The gravitational perturbation at closest approach might have pushed the already unstable primary star over the edge into the eruption. If this is correct, then the 843 event was not purely a single-star instability, but a consequence of the binary interaction, and the recurrence of such eruptions might be connected to the orbital dynamics in ways we have not yet fully modeled. What is the current state of Eta Carinae? Since the great eruption faded in the late 19th century, the star has been gradually re-brightening. By the 1990s, it had returned to naked eye visibility. In the last few decades, it has brightened further, now sitting around 4th to 5th magnitude, visible to the naked eye under dark skies. This brightening is partly because the homunculus nebula has been thinning as it expands, allowing more of the star's light to escape. But there are also indications that the star itself has increased in luminosity over the past century, suggesting that it is undergoing ongoing evolution. Eta Carinae is also variable. Its brightness changes on timescales ranging from days to years, with a prominent periodic variation tied to the five-year orbital period of the binary system. Near Periastron, the closest approach of the companion, there is a dramatic spectroscopic and photometric event as the stellar wind collision region is disrupted and reformed. These Periastron events occur like clockwork and allow astronomers to study the system's dynamics with considerable precision. The next Periastron passages are calculable decades in advance. So what do we know about the current physical state of Eta Carinae, and what does it tell us about when it will explode? The current mass of the primary star is estimated at between 100 and 150 solar masses, reduced from perhaps 170 or more at its formation by the mass loss in the Great Eruption and in the stellar winds that have been blowing since. This is an extraordinarily massive star. The most massive stars known top out at around 150 to 200 solar masses. Eta Carinae is near the top of the mass distribution. At that mass, with that luminosity, burning through its nuclear fuel at a rate that makes our sun look frugal, the remaining lifetime of Eta Carinae before core collapse is estimated at somewhere between a few thousand and a few 100,000 years. The uncertainty is large because the final stages of massive stellar evolution are extremely sensitive to parameters that are difficult to determine precisely: the current helium and heavy element content of the core, the current rate of mass loss, the influence of the binary companion on the primary's evolution, and the specific nuclear reaction rates operating in the interior. Some estimates put the time to core collapse at as little as a few thousand years. Others allow for up to 100,000. The most responsible thing I can say is that Eta Carinae is in the late stages of stellar evolution that precede core collapse, that those stages are shorter than any cosmologically significant timescale, and that on the scale of the universe's history, Eta Carinae is a dying star. Now I want to address directly the question of whether its death poses a threat to Earth, because this is where the popular accounts most often go wrong, either overstating the danger in ways that generate unjustified fear, or dismissing it in ways that misrepresent the actual physics. The threat is real but probabilistic, and the probabilities depend on two key unknowns. The first is whether the collapse of Eta Carinae will produce a gamma-ray burst at all. The second is whether Earth is in the beam if a gamma-ray burst does occur. On the first question, most core collapses of massive stars do not produce gamma-ray bursts. They produce ordinary supernovae. The formation of a gamma-ray burst requires a specific set of conditions. The collapsing core must be rotating rapidly enough to form a spinning black hole or millisecond magnetar surrounded by an accretion disk. The rotation must be sufficient to launch the jets that produce the gamma-ray burst. And the envelope of the star, the outer layers, must be thin enough or stripped enough that the jets can punch through to the surface without being absorbed. If the envelope is too thick, the jets are smothered. The gamma-ray burst never makes it out. The star produces a supernova or possibly a failed supernova, but not a gamma-ray burst. Whether Eta Carinae meets the conditions for a gamma ray burst is uncertain. On one hand, it is extremely massive and extremely luminous, and it has been losing mass through the Great Eruption and through its stellar winds for centuries. The extensive mass loss may have stripped enough of the outer envelope to allow jets to emerge. On the other hand, the mass it has lost has not necessarily been removed from the system. The homunculus nebula is still there, surrounding the star, and material from it could be accreted back onto the star or could obstruct the jets. The binary companion may influence the rotation of the primary in ways that either enhance or reduce the likelihood of a gamma ray burst. The calculations are complex and the models are not yet definitive. Some researchers estimate that the probability of Eta Carinae producing a gamma ray burst rather than a standard supernova is somewhere between 10 and 50%. Others place it higher, citing the star's extreme mass and its position near the LBV to Wolf-Rayet transition, a stage in which rapid rotation and intense stellar winds are common. Nobody places the probability at zero. Eta Carinae is the most likely nearby source of a gamma ray burst in the galaxy, and the physics that makes it likely is well understood, even if the specific probability is not. On the second question, whether Earth is in the beam, this depends on the orientation of Eta Carinae's rotation axis relative to the Earth Eta Carinae direction. Gamma ray burst jets are typically beamed within an opening angle of a few degrees around the rotation axis. For Earth to be in the beam, Eta Carinae's rotation axis would need to be aligned within a few degrees with the line from Eta Carinae to Earth. This alignment could go either way. If the axis is pointed away from us, we receive no direct gamma ray burst, only the isotropic radiation from the supernova, which at 7,500 light years is spectacular but not threatening. Observations of the homunculus nebula provide indirect evidence about the orientation of the system's rotation axis. Because the bipolar lobes of the homunculus are aligned with the rotation axis of the primary star. The axis of the homunculus, measured from its observed morphology and kinematics, appears to be tilted at approximately 40 to 45 degrees relative to the line of sight from Earth. This is encouraging for Earth safety because it suggests the main beam of any gamma ray burst would be directed away from us. But the uncertainty in this measurement is significant. The jets need not be perfectly aligned with the rotation axis, and there is some evidence that the secondary star's orbital plane is tilted differently from the primary's rotation axis, introducing additional complexity. The current scientific consensus, to the extent that consensus exists on a question with this many uncertainties, is that Earth is probably not in the direct beam of any gamma ray burst that Eta Carinae might produce. Probably, not certainly. The evidence is suggestive but not conclusive. And the consequences of being wrong, of being in the beam, are significant enough that the question deserves continued study. Let me put the risk in perspective by connecting it to the geological record. There is a hypothesis that has been debated for several decades, never definitively confirmed or refuted, that a gamma ray burst from a nearby star was responsible for the late Ordovician mass extinction, which occurred approximately 445 million years ago and killed roughly 85% of all marine species. The late Ordovician extinction is the second largest mass extinction in Earth's history, surpassed only by the Permian-Triassic event that killed 90% of all species 252 million years ago. The cause of the late Ordovician extinction has been debated since it was first clearly identified in the fossil record. The standard explanation involves glaciation, a rapid and severe ice age that lowered sea levels, reduced habitat, and disrupted ocean chemistry. This explanation is well supported by evidence of glacial deposits in what was then Gondwana. But some aspects of the extinction pattern are puzzling on purely glaciological grounds. The extinction preferentially affected species that lived near the surface of the ocean, in the upper photic zone where sunlight penetrates. Species living in deeper waters, where sunlight is already weak, survived better. This pattern is exactly what you would expect from an event that increased the flux of ultraviolet radiation at the ocean surface, as would happen following ozone depletion from a nearby gamma ray burst. Additionally, the extinction happened in two distinct pulses: a rapid initial extinction that killed off many surface-dwelling species, followed by a recovery, followed by a second extinction pulse correlated with the advance of glaciation. The two-pulse structure is consistent with a gamma ray burst scenario in which the initial pulse of ozone depletion kills surface-dwelling species, the ozone recovers over years to decades, and then the cooling caused by the disruption of photosynthesis contributes to glaciation that drives the second pulse. Astrophysicists who have studied this hypothesis note that the rate of gamma ray bursts from sources within the range required to cause this level of ozone depletion is roughly consistent with the observed geological record of mass extinctions. There have been approximately 5 major mass extinctions in the past 500 million years. The rate of nearby gamma ray bursts over that period, estimated from the population of massive stars and their death rates in our galactic neighborhood, is also approximately 5 to 10 events within the relevant range. The numbers are at least roughly compatible. I want to be careful about what I am claiming here. The gamma ray burst hypothesis for the late Ordovician extinction is a serious scientific proposal, supported by several lines of indirect evidence and consistent with the physics, but it is not proven. The glaciological explanation remains more widely accepted among paleontologists, and there are aspects of the late Ordovician record that the gamma ray burst hypothesis does not easily account for. The truth may involve both: a gamma ray burst that initiated the ozone depletion and contributed to the rapid initial extinction, combined with glaciation that drove the subsequent phases. Or the truth may be purely glaciological, with the gamma ray burst connection a coincidence or a misinterpretation of the evidence. I want to be careful about what I am claiming here. The gamma ray burst hypothesis for the late Ordovician extinction is a serious scientific proposal supported by several lines of indirect evidence and consistent with the physics, but it is not proven. The glaciological explanation remains more widely accepted among paleontologists, and there are aspects of the late Ordovician record that the gamma ray burst hypothesis does not easily account for. The truth may involve both: a gamma ray burst that initiated the ozone depletion and contributed to the rapid initial extinction, combined with glaciation that drove the subsequent phases. Or the truth may be purely glaciological, with the gamma ray burst connection a coincidence or a misinterpretation of the evidence. Let me describe the evidence that proponents of the gamma ray burst hypothesis find compelling, because I think it deserves a fair hearing. The first line of evidence is the geographic distribution of survivors. In most mass extinctions caused by a single global catastrophe, the pattern of survival and extinction should be roughly random with respect to geography. Species living in different latitudes should have similar survival probabilities if the cause is global. But in the late Ordovician, there is a marked latitude dependence in the extinction pattern. Species living at high latitudes, where the intensity of ultraviolet radiation would be least if the ozone layer were depleted, showed somewhat better survival than species living at low latitudes, where ultraviolet would be most intense. This latitude dependence is exactly what you would expect from an ozone depletion event, and it is less easily explained by glaciation alone, which would preferentially affect high latitude species. The second line of evidence is the specific groups that went extinct. The late Ordovician extinction was particularly severe for organisms living near the surface of the ocean in the photic zone where sunlight penetrates. Trilobites, brachiopods, and graptolites living near the surface were hit much harder than organisms living in deeper water or on the ocean floor. Surface-dwelling organisms are precisely those most dependent on photosynthesis, and most exposed to ultraviolet radiation. The pattern of extinction by depth and by dependence on sunlight is consistent with the ozone depletion scenario. The third line of evidence is the timing. The initial rapid phase of the late Ordovician extinction was geologically sudden, occurring over a period estimated at less than 1 million years and possibly much shorter. This speed is difficult to explain by gradual glaciation alone. A gamma-ray burst event would be instantaneous on geological timescales, with the ozone depletion occurring over days to weeks and the elevated ultraviolet flux persisting for years to decades. The subsequent cooling and glaciation could then drive the second phase of extinction over the longer timescales that glaciation requires. None of this proves the gamma-ray burst hypothesis. Correlation is not causation, and alternative explanations exist for each piece of evidence. The rapid initial phase might reflect the speed of glaciation rather than a burst event. The depth-dependent survival might reflect the different temperature tolerances of shallow and deep water species rather than ultraviolet sensitivity. The geographic pattern might reflect the location of glacial refugia rather than latitude-dependent ultraviolet exposure. The scientific community has not reached a consensus that the gamma-ray burst hypothesis is correct, and I would be misrepresenting the state of the evidence if I presented it as proven. What I can say is that the physics is plausible, the numbers are at least roughly compatible, and the hypothesis is taken seriously by a significant number of researchers in both astrophysics and paleontology. The history of life on Earth may have been punctuated by gamma-ray bursts from nearby stars. And if that is true, it means that the cosmic environment, the specific population of massive stars in our galactic neighborhood and their death rates, has played a role in shaping the trajectory of evolution on this planet. This is a profound conclusion. It means that the history of life is not just a story of biology, of natural selection operating on heritable variation in an environment defined by the physical conditions on Earth's surface. It is also a story of astrophysics, of the cosmic neighborhood, of the specific stars that have lived and died within range of Earth's biosphere over the past 4 billion years, the specific mass extinctions that cleared ecological niches and opened opportunities for new lineages are not purely geological or biological events. They may be partly astronomical events, consequences of the violence of massive stellar deaths in our corner of the galaxy, and you are one of the consequences, not directly. The chain of causation between any ancient gamma-ray burst and your existence is too long and too complex to trace. But the mass extinctions that shape the trajectory of evolution on Earth, eliminating some lineages and creating opportunities for others, are part of the context in which your species emerged. If the late Ordovician extinction had gone differently, if the specific extinctions and survivals had been different, the trajectory of evolution over the following 445 million years would have been different. The probability that it would have produced anatomically modern humans is impossible to estimate, but it would not have been the same. The cosmic violence that Eta Carinae will eventually produce is not separate from the story of life on Earth. It is a continuation of the same processes that have been shaping that story for hundreds of millions of years. Let me now step back and consider Eta Carinae in the broader context of our galactic neighborhood, because it is not the only potentially dangerous star in our vicinity. It is the most extreme, the most carefully studied, the most likely to produce a gamma-ray burst, but there is a population of massive stars in the several thousand light-year sphere around our solar system that are all, to varying degrees, aging toward violent deaths. Betelgeuse, the red supergiant that forms the left shoulder of the constellation Orion, is one of the most famous. It is approximately 700 light-years from Earth, much closer than Eta Carinae, and it is a massive star in the late stages of evolution, burning through its remaining nuclear fuel and expected to undergo a supernova within the next 100,000 years, possibly much sooner. When it explodes, it will be visible in daylight. it will cast shadows at night. For weeks or months, it will be one of the most dramatic astronomical events in recorded history. But at 700 light years, even in the most pessimistic scenario, it does not pose a significant gamma-ray burst threat to Earth. The distance is sufficient that the gamma-ray fluence, even if Betelgeuse produced a burst aimed directly at us, which is unlikely given its rotation axis orientation, would be well below the threshold for significant ozone depletion. But Betelgeuse illustrates the general principle. We live in a galaxy that is continuously producing massive stars, which live fast and die violently. Many of those deaths happen in our galactic neighborhood. The death of a star within a few thousand light years is not an exotic rarity. Over the lifetime of the Earth, hundreds or thousands of stars within that range have undergone core collapse. Most produced ordinary supernovae. A small fraction may have produced gamma-ray bursts. Of those, an even smaller fraction may have had beams aimed at Earth. The probability per event is small, but the number of events over 4 billion years is large. The cumulative probability that at least one nearby gamma-ray burst has intersected Earth during its history is not negligible. The Orion molecular cloud, the stellar nursery that produced the stars of the Orion constellation and is currently forming new stars at a distance of approximately 1,300 light years from Earth, contains several O-type stars, the most massive and most luminous classification that are expected to undergo core collapse within the next few million years. These include stars in the Orion OB1 association, a loose group of massive young stars that are already aging toward their violent ends. None of them is as extreme as Eta Carinae. None is as carefully studied. But each represents a potential future supernova or gamma-ray burst source within the relatively nearby cosmic environment. Looking further out, the galaxy contains a population of Wolf-Rayet stars, stars that have shed their outer hydrogen envelopes through intense stellar winds and are in the final stages before core collapse, that are distributed throughout the galactic disk at distances ranging from a few hundred to tens of thousands of light years. Wolf-Rayet stars are the most likely progenitors of long gamma-ray bursts because their stripped envelopes allow the jets to escape without being absorbed. A Wolf-Rayet star within a few thousand light years of Earth, with its rotation axis aimed at us, represents exactly the kind of source that the late Ordovician hypothesis envisions. And while no such star is currently as well characterized as Eta Carinae, the population is large enough that the cosmic risk from gamma-ray bursts is not dominated by any single object. Looking further out, the galaxy contains a population of Wolf-Rayet stars, stars that have shed their outer hydrogen envelopes through intense stellar winds and are in the final stages before core collapse, that are distributed throughout the galactic disk at distances ranging from a few hundred to tens of thousands of light years. Wolf-Rayet stars are the most likely progenitors of long gamma-ray bursts because their stripped envelopes allow the jets to escape without being absorbed. A Wolf-Rayet star within a few thousand light years of Earth, with its rotation axis aimed at us, represents exactly the kind of source that the late Ordovician hypothesis envisions. And while no such star is currently as well characterized as Eta Carinae, the population is large enough that the cosmic risk from gamma-ray bursts is not dominated by any single object. There are a few Wolf-Rayet stars in our galactic neighborhood that deserve specific mention. WR-104, located approximately 8,000 light-years away in the constellation Sagittarius, is a Wolf-Rayet star in a binary system with what appears to be a highly face-on orbit. The face-on orientation of the orbit, combined with the fact that Wolf-Rayet stars tend to rotate rapidly and to have their rotation axes aligned with their orbital axes, raises the possibility that WR-104's rotation axis points toward Earth. If it does, and if it produces a gamma-ray burst, when it undergoes core collapse, Earth would be in the beam. Detailed observations with the Keck telescope in the early 2000s by Peter Tuthill and colleagues revealed a spectacular pinwheel nebula around WR104, produced by the interacting stellar winds of the binary system that allowed a precise determination of the orbital geometry. Their analysis found that the orbital axis is inclined at approximately 16 degrees from the line of sight to Earth, meaning Earth is close to, though probably not exactly in, the beam of any future gamma ray burst. WR104 is not as extreme as Eta Carinae. It is not as massive, not as luminous, not as unstable, but it is a Wolf-Rayet star, the category most associated with gamma ray burst production, and its orbital geometry raises a flag. The scientific consensus, based on Tuthill's observations and subsequent analysis, is that the exact alignment required for Earth to be in the direct beam is unlikely but not impossible. The situation warrants monitoring. Another example is WR42e, a recently discovered Wolf-Rayet star in the galactic plane at a distance of approximately 6,000 light-years. Its rotation axis orientation is not as well constrained as WR104's, but its proximity and its evolutionary stage make it worth noting. There are several other Wolf-Rayet stars within 10,000 light-years of Earth whose orientations and evolutionary states are not yet sufficiently characterized to assess their specific threat level. The general point is this: there is not just one potentially dangerous star in our neighborhood. There is a population of massive stars in various stages of their violent final phases, distributed through our galactic environment, some of them with geometric alignments that put Earth in or near the potential beam of any gamma ray burst they might produce. Eta Carinae is the most extreme member of this population. It is the most likely to produce a gamma ray burst of sufficient energy to affect Earth, but it is part of a broader cosmic risk environment that has been present throughout Earth's history. The solar system is not in a static, safe environment. It is embedded in the galactic disk, surrounded by massive stars at various stages of their evolution, moving through regions of different stellar density as it orbits the galactic center, occasionally passing through spiral arms, where star formation rates are higher and the density of massive stars is greater. The cosmic environment of Earth is dynamic, changing on timescales of tens of millions of years as the solar system moves through different regions of the galaxy, and it has not always been as benign as it is now. I want to say something about what all of this means for the question of life in the universe, because Eta Carinae and the broader population of massive stars near Earth tells us something important about the cosmic filter that shapes where complex life can develop and persist. Astrobiologists studying the conditions for life in the Milky Way have developed a concept called the galactic habitable zone. The idea is that not all regions of the galaxy are equally hospitable to complex life. The galactic center has a very high density of stars, a very high rate of supernovae and gamma ray bursts, and strong radiation environments that may make complex life difficult. The outer edge of the galactic disk has insufficient heavy elements because those elements are built up by generations of stellar nucleosynthesis that has proceeded faster in the inner galaxy. The most hospitable region is a ring in the middle of the disk, at a galactic radius similar to the Sun's, where the density of massive stars is moderate. The abundance of heavy elements is sufficient for complex chemistry, and the rate of gamma ray bursts is low enough that complex ecosystems can develop and persist over billion-year timescales without being sterilized. Our solar system sits in this galactic habitable zone, not by coincidence, but by anthropic reasoning. We exist in a region where complex life was possible because we could not exist in a region where it was not. But the existence of the galactic habitable zone, the fact that only certain regions of the galaxy are hospitable to complex life, has implications for the frequency of life in the universe. If the galactic habitable zone is a small fraction of the galactic disk, and if similar constraints apply in other galaxies, then complex life may be less common than simple calculations based purely on the abundance of stars and planets would suggest. The cosmic violence that Eta Carinae exemplifies is not just a local curiosity. It is one of the factors that limits the cosmic distribution of complexity. Our solar system sits in this galactic habitable zone, not by coincidence, but by anthropic reasoning. We exist in a region where complex life was possible because we could not exist in a region where it was not. But the existence of the galactic habitable zone, the fact that only certain regions of the galaxy are hospitable to complex life, has implications for the frequency of life in the universe. If the galactic habitable zone is a small fraction of the galactic disk, and if similar constraints apply in other galaxies, then complex life may be less common than simple calculations based purely on the abundance of stars and planets would suggest. The cosmic violence that Eta Carinae exemplifies is not just a local curiosity. It is one of the factors that limits the cosmic distribution of complexity. The galactic habitable zone concept was developed in detail by Charles Lineweaver and his collaborators in the early 2000s. Their analysis combined several factors: the gradient of heavy element abundance across the galactic disk, the rate of supernovae and gamma ray bursts as a function of galactic radius, the stability of planetary orbits in different parts of the galaxy, and the timescales for biological evolution. The result was a ring-shaped region of the galactic disk, centered at a galactic radius somewhat larger than the Sun's current position, that represents the optimal environment for complex life. The Sun is approximately in the middle of this zone, which is one reason it has been able to sustain a biosphere for 4 billion years. But the boundaries of the galactic habitable zone are not sharp. They reflect statistical averages. Within the habitable zone, there are still regions of locally enhanced stellar density where gamma ray burst rates are higher. There are still occasional passages through spiral arms where the density of massive stars increases temporarily. And there are still individual objects, like Eta Carinae, that pose specific directional threats, even at considerable distances. The galactic habitable zone tells you where, on average, the conditions are favorable. It does not guarantee safety from every specific source of cosmic violence. The concept also evolves over cosmic time. The galaxy was a different place 10 billion years ago, with a much higher rate of star formation, a much higher density of massive stars in the disk, and a much higher rate of gamma ray bursts. Early in galactic history, the cosmic violence was more intense and more widespread. The galactic habitable zone, if it existed at all in the early galaxy, was probably much smaller. Complex life that required billions of years of uninterrupted biological evolution to develop may simply not have been possible in the early galaxy, not because the chemistry was wrong or the planets were absent, but because the rate of sterilizing events was too high. This has an interesting implication for the search for extraterrestrial intelligence. If complex life requires billions of years of relatively undisturbed biological evolution, and if the cosmic violence of the early galaxy made that impossible until relatively recently, then the maximum age of technological civilizations in the Milky Way may be limited. Not because intelligence is rare, but because the conditions that allow it to persist have only recently become favorable over a significant fraction of the galactic disk. The apparent silence of the cosmos may be partly a consequence of the cosmic violence that shapes the galactic habitable zone. Let me come back to Eta Carinae one more time, and to the specific moment we are in with respect to this extraordinary object. The light we see from Eta Carinae tonight left the star approximately 7,500 years ago. At that time, the great eruption of 1,843 had not yet occurred. The star we are looking at in the sky is the star as it was before its most recent dramatic eruption. The actual star, right now, in the sense of the star as it exists at the moment you are reading this, is 7,500 years further along in its evolution. It may have undergone another eruption. It may have shed more mass. It may be significantly closer to its final collapse than the light we are currently receiving reveals. This is not a hypothetical. It is a consequence of the finite speed of light that I discussed in the video about the permanence of the past. The star we observe is not the star that exists. It is a record of the star as it was. The actual star at the temporal location of this moment is inaccessible to us. We will not know what it has done in the last 7,500 years until the light from those events reaches us. And the light from Eta Carinae's core collapse, when it occurs, will take 7,500 years to reach us. We may have already missed the warning, or the warning may have been sent and is currently racing toward us at the speed of light due to arrive in a few hundred or a few thousand years. We will not know until it arrives. And when it arrives, the light from the explosion will reach us before the gamma radiation, because the visible light travels at the speed of light, and the gamma ray burst, if there is one, also travels at the speed of light. But the initial flash of visible light and the gamma ray emission are produced at slightly different times and in slightly different ways. In practice, the warning time between the first optical brightening of the supernova and the arrival of any gamma ray burst would be seconds to minutes, far too short for any practical response. I want to address directly the question of what, if anything, we should do about the possibility that Eta Carinae poses a genuine threat. The answer is complicated by the timescales involved. If Eta Carinae is going to explode within the next 1,000 years, the civilizations and technologies that exist at the time of the event will be so different from what exists today that planning a response now is essentially meaningless. The question of what technology a civilization 10 centuries in the future will have available is impossible to answer from the vantage point of the present. It would be like the ancient Romans planning a response to the Industrial Revolution. If the event is hundreds of thousands of years away, the situation is even more extreme. On those timescales, the evolution of the species, of technology, of civilization is so unpredictable that the concept of advanced planning barely applies. What does apply right now, in the present, is understanding. The value of understanding the threat posed by Eta Carinae is not primarily in enabling us to build some kind of shield or deflection system. It is in contributing to the broader scientific understanding of the cosmic risk environment, of the role of massive stellar deaths in the history of life on Earth, of the physics of gamma ray bursts and their interactions with planetary atmospheres. That understanding is valuable in itself, as all scientific understanding is valuable, and it contributes to the slow, patient accumulation of knowledge about the universe that is the most specifically human activity I know of. But there is also a more practical dimension to the understanding. We are currently in the early stages of developing what you might call cosmic situational awareness, the ability to monitor, characterize, and track the potentially threatening objects in our astronomical environment. For the threat from near-Earth asteroids, this awareness is already fairly well developed. We have extensive survey programs tracking near-Earth objects, estimating their orbital parameters, calculating their impact probabilities decades in advance. We have rough plans, if not yet deployable technology, for deflecting objects on collision courses. For the threat from massive stellar deaths, our awareness is much more rudimentary. We can identify the most massive and most evolved stars in our galactic neighborhood. We can study their current physical states in considerable detail using space-based telescopes across the electromagnetic spectrum. We can make probabilistic estimates of their remaining lifetimes and their potential to produce gamma ray bursts, but we cannot predict the exact timing of their collapse with anything approaching the precision we can achieve for asteroid impacts. We cannot predict whether a given star will produce a gamma-ray burst or an ordinary supernova, and we cannot deflect or otherwise influence the outcome. What we can do is continue to develop our understanding of the physical processes involved. The detailed study of Eta Carinae, its spectroscopic monitoring across the orbital cycle, its imaging at multiple wavelengths, the modeling of its internal structure, and its binary interaction. All of this feeds into a better understanding of how such stars evolve and die. Each new observation constrains the models. Each model improvement gives us a better ability to assess the current state of the star and make more informed estimates of its future behavior. There is also value in developing better detectors for the early warning signals of a massive stellar collapse. Neutrino detectors, which can detect the burst of neutrinos from a core collapse hours before the visible brightening reaches us, are an important component of this infrastructure. The existing network of large neutrino detectors, including Super Kamiokande in Japan, IceCube at the South Pole, and several others, is specifically configured to detect and localize a nearby supernova neutrino burst. A supernova early warning system, known as SNEWS, has been in operation since 2005, coordinating the neutrino detectors to provide rapid automated alerts when a coherent burst is detected across multiple instruments. When Eta Carinae undergoes core collapse, the SNEWS system will know about it hours before the light arrives. What happens in those hours? Honestly, not much that matters practically. But scientifically, the advance warning would be extraordinary. Telescopes around the world and in space would be pointed at Eta Carinae. Every wavelength would be covered. The early stages of the explosion, before the visible light has diffused out through the stellar envelope, would be observed with unprecedented coverage. The neutrino data itself would reveal information about the physics of the collapsing core. And if a gamma-ray burst follows, the direction of the beam could be quickly determined, and the potential threat to Earth could be assessed in real time. I want to acknowledge something that I have been somewhat carefully sidestepping, which is the emotional content of what I have been describing. Eta Carinae is a specific, visible, named object that poses a specific, characterized threat to the biosphere of our planet. The threat is probabilistic, the timescales are vast, but it is real. And sitting with the knowledge that there's a star out there, burning right now, moving toward an explosion that could harm life on Earth, is a different kind of knowledge than abstract statistical risk. It is the knowledge of a specific adversary, even if that adversary is indifferent and impersonal and unaware of our existence. I think this kind of knowledge deserves acknowledgement rather than suppression, not alarm. Not fear, but honest acknowledgement that we are not alone in the galaxy in the sense that the galaxy contains processes and events and objects whose consequences extend to us. We are not isolated. We are embedded in a larger physical system whose dynamics include events of enormous violence, and some of those events can reach us. The appropriate response to this knowledge, I think, is neither panic nor dismissal. It is the same response that is appropriate to any knowledge about the structure of reality, curiosity, study, and the ongoing project of understanding the universe we inhabit. And there is something more. The recognition that Eta Carinae exists, that it poses a specific, characterized, physically understood threat to life on Earth on astronomical timescales, is a reminder that we are not in a protected, privileged environment. We are in the galaxy. We are surrounded by massive stars whose deaths can affect us. The boundary between the cosmos and the biosphere is not a wall. It is permeable in both directions. The cosmos made us through the nucleosynthesis of the elements and the formation of the solar system and the long geological and biological processes that produced complex life. And the cosmos can, in principle, unmake what it made through the same violent processes that are part of the ongoing life cycle of stars. This is not a reason for despair. It is a reason for perspective. The specific combination of circumstances that has allowed complex life to develop on Earth for 4 billion years, the distance from the galactic center, the composition of the solar system, the orbital stability of the planets, the current quiescence of the local stellar environment, is not guaranteed to continue indefinitely. It has been favorable for a long time. It will remain favorable for the foreseeable future. But on the longest timescales, the cosmic environment is not fixed. It evolves. The stars around us evolve. Eta Carinae will collapse. Other massive stars will follow. The galactic neighborhood we inhabit is not the same neighborhood our distant descendants will inhabit. And knowing that, understanding that, is itself a form of what the universe has been building toward over its entire history. A configuration of matter capable of looking at the sky and understanding not just the beauty of the stars, but the physics of what they are, how they live, how they die, and how their deaths connect to the history of life and the future of the cosmos. I find something genuinely moving about this, not in a sentimental way, in a physical way. The fact that the universe has produced in the specific branch of stellar and biological and cognitive evolution that led to us entities capable of characterizing the threat from Eta Carinae is itself one of the most extraordinary things that has happened in this solar system in 4 billion years of cosmic history. The atoms in your brain that are processing this information, the carbon and oxygen and nitrogen that were assembled in stellar cores and dispersed in supernova explosions before being incorporated into the molecular cloud that formed the sun, are processing information about the very processes that produce them. The children of stellar nucleosynthesis are studying the death of stars. The beneficiaries of cosmic violence are understanding the nature of the violence that made them possible. There is a recursive depth to this that I find remarkable. Eta Carinae's predecessor stars, the generations of massive stars that lived and died before Eta Carinae formed, contributed the heavy elements that eventually made their way into the solar nebula and into the planets and eventually into the chemistry of life. The violence of those earlier stellar deaths is part of what we are made of. And now we study Eta Carinae, a current generation of that same process, understanding it, characterizing it, calculating its potential threat to the very life that earlier stellar deaths helped make possible. The universe is not doing this to us deliberately. Eta Carinae is not aware of our existence. The processes of stellar evolution are indifferent to the specific chemistry that emerged on a small planet 7,500 light years away. But the physics is the physics. The nucleosynthesis is real, the threat is real, and the understanding is real. All three emerge from the same underlying physical process, the life cycle of massive stars in the Milky Way operating at different scales and different levels of complexity. Go outside tonight if you are in the southern hemisphere, or if you have a clear view of the southern horizon from lower latitudes in the north, look for the constellation Carina. Find Eta Carinae. It is a faint, naked eye object now, a star among thousands, unremarkable at first glance, but it is not unremarkable. It is one of the most massive objects in our galaxy. It has already erupted in an event that made it the second brightest star in the sky. It will explode with certainty within the next 100,000 years. And when it does, the flash of light from that explosion will be visible in daylight for weeks. It will outshine the full moon. It will be the most spectacular astronomical event in the history of our species. And if the conditions are right, if the geometry is wrong for us, the beam of gamma radiation that follows the visible light will arrive here and begin, quietly and invisibly, to dismantle the ozone layer that makes this planet habitable. The star you are looking at already contains the end of that story within it. The iron core is building. The silicon is burning or will burn soon in the deep future. The equilibrium is unstable. The collapse is coming. We know which star it is. We know the physics. We know the threat. And that knowledge, the specific, hard-won, mathematically precise knowledge of what is out there and what it will do, is one of the most extraordinary things that the entropy gradient of this universe has produced in its 4 billion years of biological experiment on this particular planet. Consider what it would have meant to any civilization in human history to have this knowledge. The ancient Greeks, whose natural philosophy first attempted systematic explanation of celestial phenomena, had no concept of nuclear fusion, no understanding of stellar evolution, no framework for understanding why stars shine or how they die. When they looked at the sky, the stars were fixed points of light, eternal, unchanging, the abode of the gods. The idea that those points of light were spheres of plasma powered by nuclear reactions, burning through their fuel on their way to violent deaths that could affect planets thousands of light years away, was simply not available to them. Medieval astronomers were better equipped mathematically, but still had no physical theory of stellar structure when supernovae appeared in historical records. The Chinese observation of the Crab Nebula supernova in 1054, the Danish astronomer Tycho Brahe's observation of a supernova in 1572, these were interpreted as new stars appearing in the supposedly unchanging celestial sphere. The idea that they were the violent deaths of massive stars, deaths that released more energy in days than the sun would release in billions of years, was beyond the conceptual reach of the observers. Even 19th century astronomers, observing the great eruption of 1843 in real time, had no framework to understand what they were seeing. They knew something extraordinary was happening. But the nuclear physics that explains why it happened, the stellar evolution models that tell us it is a luminous blue variable approaching the end of its main sequence phase, the binary dynamics that may have triggered the eruption, all of this required a century of physics development before it became available. We are the first generation of beings on this planet to have this knowledge. The first to understand what Eta Carinae is, what it will do, and what the consequences could be. That is not a burden. It is a privilege. A specific, hard-won, remarkable privilege that comes from 400 years of systematic, scientific investigation of the physical world. And the knowledge, once acquired, belongs to whoever understands it. It belongs to everyone who learns the physics and follows the argument. The star that will threaten our solar system already exists. It is out there tonight, burning, unstable, moving toward its end. The star that will threaten our solar system already exists. It is out there tonight, burning, unstable, moving toward its end, and we know exactly which one it is. That, I think, is worth knowing. If this changed how you think about the night sky, if Eta Carinae looks different to you now than it did before you knew what it was, tell me in the comments. Tell me what piece of this physics you find most important to understand and why. And subscribe if you want to keep going deeper into the places where stellar astronomy and the history of life on Earth intersect in ways that nobody told you about in school.